Сегодня у
everyone.
нас второй воркшоп.
We have second workshop today
Второй воркшоп нашего HackAtom RU.
of our HackAtom.ru, the first ever hackathon in the Russian language. Today we have Sergey Prilutzki speaking for you. You know him full well. So he's going to be talking about the performance of blockchain, how to measure it properly, a whole bunch of tools, technologies. All of this is the scope for today. Sergey is online, right? The only thing I need to tell is, guys, feel free to ask questions to Sergey. He'll be able to respond to them at the end of our workshop. Now, to ask a question, please make sure you send it right here into the Telegram channel. I will be checking it out, reading it, monitoring as we speak, and then I will voice all the questions you guys send to us using my voice. Right. So, YouTube, possibly, if you're watching this in English, you're on Cosmos YouTube channel, you can also use that chat to ask questions in English. It's no problem. So, participate in the hackathon, listen to all the workshops. Sergey, the floor is yours. Hey there. Hi, guys. It's a pleasure to deliver this workshop for you, to talk about this challenging story, testing changes, testing the performance of blockchain. Because, well, quite a few people know me, but just for the sake of politeness, let me introduce myself. I'm head of research with MixBytes. We do auditing of smart contracts. We write those ourselves. We develop those ourselves. We develop blockchains. We're the official delivery partner of Polkadot system. We've been managing pretty much every big blockchain. OS Polkadot, Cosmos, we supervise it as a project as well. Now, in part, one of our objectives was testing the performance of the Polkadot network. We got a grant specifically to that end. And this is what I've been meaning to tell you, the kind of pitfalls that we've identified, the lessons learned, and I would like to use this workshop to say that testing blockchain performance is a challenging task. So this is pretty much the content of the workshop. That's it in a nutshell. That's our clients, partners. So the PR time is, the ad block is about to finish. Right, down to business. I'm going to have several links I'll be referring to as we go, but I'll provide them. So the first thing, where does the blockchain testing system coming from? Let me start from afar. If you're writing a blockchain on Cosmos, I don't know, you're creating your blockchain on Polkadot. So these are fairly similar projects in terms of product development. Then the answer to this question, how quick, how fast your blockchain is, how many TPS it leverages, well, this is a bit of an amateurish question, because this notion, transactions per second, or TPS, is essentially quite tricky. It depends on dozens, even hundreds of multiple factors. So asking what's your mean TPS, well, you'll get a give or take 80–90%, plus or minus, up or down. So it could be 10 times more, it could be 10 times less from the figure you get. So this is very well in line, in tune with distributed databases. Let me do some drawing for you, paint you a little picture. This is a classical situation when your DB is failing, you have too many clients coming in from all over the globe, and you got tons of servers of DBs hosted in various geographic locations possibly, and you start facing the first scaling problems. If, say, it's a banking problem, then the time zone in Europe, there is, like, say, Vasya with $100 on his account. So he buys a bicycle in Europe, and he's buying something else in China using the same amount. Since these servers, well, for them to interact, who's going to be the first, which transaction to prioritize, who came first, which one came first, the bicycle or something else in China. So this needs to be coordinated and approved. If it's not run simultaneously, this will be an issue. If Vasya might face a problem, he'll spend the money twice. Like a dual purchase in this area will get detected only later. or Vasya will stand here and wait until the network distributes that his $100 was spent in the first instance. He'll need to wait for the signal to reach Europe, then China, then US, and only when all the changes have been coordinated, he will get the approval of his transaction. So in this respect, blockchains are very similar to distributed databases. And even more accurate approximation is these systems that spread the information, that spread the data across the nodes. These systems are referred to as replication systems. So how is our information replicated, as in copied, simultaneously to all the nodes? This is a master-master replication, MM replication. Master-master because the master is the database that is handling addition, removal, modification of data. So any kind of modification is done by this master DB. Then dozens and hundreds of databases can come into play who are not recording the information, but they're just offloading the information to the clients, shipping the information to the clients, because writing happens times less frequently than receiving of the information. Like request of information, requests for reading the information are much more frequent than the requests for writing. These master-master systems are fairly slow, sluggish. Well, obviously, one super server that does not need to coordinate anything with other servers works much faster. So the conventional scaling schemes for databases scale up. That's master-slave. So there is a master server. That information from it is copied to slave servers, and those servers are in turn shipping off this information very rapidly. Master-slave and master-master, part of the participants here could be Byzantine. Byzantine as in participants that intentionally misbehave. So roughly speaking, huge DBs and their replication systems allow for the system to operate even if one node gets disconnected from the network or starts doing something off the book. But they're not protected from intentionally malevolent behavior, misbehavior. So if this server starts saying to the American server that Vasya spent $100, and it says to the Chinese that he did not spend this $100, or said that he spent $30 out of that 100, and when they coordinate between themselves, there will be another error, coordination, syncing error, and so on and so forth. These protocols of corporate systems, they're not intended for Byzantine behavior, Byzantine behavior patterns. Consensus provides stability for blockchain, even if some part of the machines can typically, in modern consensus, if the share of misbehavior is less than 33%, the blockchain cannot be stopped. So the data cannot be messed with, cannot be tampered with. So the testing of performance of blockchain is very much in line with distributed DBs. It's more like that kind of stuff. So everything I'm about to tell you guys is applicable to distributed algorithms of replication as well. So basically, this is one and the same thing. The blockchains operate similarly. However, there are some particular features. Now, in pretty much every modern DB out there, there is this so-called wall, write-ahead log. This wall file, well, you can think of it as a file that gets recorded all the time to the disk, and it stores the transaction history in a very strictly ordered manner. Because like I said, the order of transactions is important, because Vasya was buying the bicycle in Europe, and I don't know, he was buying some game in App Store in China, or some application that required payment fee-based. So the order of transactions is important, because it's not known which purchase came first. The bicycle in Europe was some digital service in China. So these transactions are stored into the wall file, strictly ordered, and each time having applied the next chunks changes, they remember where they stopped applying. So they applied in chunks. This is similar to the nodes building chains of blocks in our blockchains, and then pile up transactions on top. So these mechanisms are very similar. I'll disclose you a secret, I'll let you in on the secret. At the level of Bitcoin, at the level of Ethereum, at least Polkadot, under the hood, they're using these very databases with the write-ahead log, specifically to this end, to make sure that the subsequent transactions are stored and then applied in a chunk, in a batch. So if we want to test something, or if you're developing a blockchain of your own, and your CEO comes over and says, all right, guys, how many TPS our blockchain does? So the right answer to that is we need the budget, we need several weeks of time, we need a good DevOps, and the automation guy, and we need a cloud with, say, various machines, dozens of dollars per month. Could be a dozen, could be 100 of those machines. There's no other way, dear CEO, to answer to your question about the TPS. Because similarly to the distributed databases, there's too many factors in play here. There's too many different situations in play here. Some nodes might lose their internet connection. Some nodes might have a disk overflow problem that they just stalled. So some servers are too weak. The hardware is too slow. The resources are limited. So there are so many various cases. For this reason, testing blockchains like this, well, it's, only real-life testing is the way to go. Like emulating the behavior of the blockchain, and the more specifically you can do that, the better. Let me explain you why. First off, all the problems emerge frequently when the problem is facing not one stakeholder but multiple, like poor network in a whole segment. Maybe some transatlantic cable is overloaded and the whole segment of the network is sluggish. Transactions are processed differently because the software is different, RAM, CPUs are different. No typical configurations exist for this kind of stuff. The information exchange is slow because blocks are fairly big chunks of data, fairly big chunks, possibly a megabyte, couple megabytes, and tossing them over from server to server across the network is not that simple. Let me just, grab this. Heavy clients. What do I mean by heavy? It means that the software operating here is very significant, is very high load. And the blockchains could not appear before the computers that can verify the dozens of thousands of digital signatures per second emerged. Otherwise, the blockchains couldn't exist. And this software is fairly heavy duty. I mean, you cannot launch it on a smartphone because it will eat away through your battery in minutes, in a matter of minutes, if you do. Resources need to be paid for and so on and so forth. So if you're developing a blockchain of your own and you've done something, you got something done, and you claim that that blockchain is going to be leveraging hundreds of thousands of transactions per second, well, that stuff still needs to be proved. The replication of the network's operation will be difficult because you will need to launch dozens of these validators. The number of validators basically determine the speed of coordination intra-network. The speed of the network will depend on how many transactions this blockchain is already managing, the state, how big the state is, the volume of the state. If that volume is huge, and possibly the computer is running memory overflow, and the performance dropped down rock bottom. There is indirect influence of some participants against the others. Some dedicated node that is currently the master one, it generates blocks, it proves to be too weak resource-wise. Something happened, or there is backup operation going on, and sluggish, slowing down significantly with block generation. The others need to put up with this. Governance, by governance I mean managing the structure of these nodes, validators, miners. This composition might change. I know if you had 20 validators and now you have 27. Of course, the processing time and so on and so forth will change because of that. Various consensus algorithms act differently depending on the type of problems they face. Some are more resilient to network downtime. Some take less time to restore after the network is back in order. Some are very reliable clients. Some sacrifice reliability. I mean, they sacrifice speed to be more reliable, to make sure that the client gets 100% consistent information. So there is a whole lot of intricacies. And the P2P, peering networks are also concealed, are also hidden there. It's very difficult to test those because it involves, well, possibly another 100 of participants will come over who are going to be provided information to everyone, and the network will be running fast. And then they might shut down in a blink of an eye. And it will take the network some time to understand that a whole bunch of nodes just went away, went out. And during that time, the network will be degrading. The network performance will be degrading. So all of this is worsened by transactions, the types of transactions. To make matters worse, how many TPS your CEO asked you was the first question. What kind of transactions? They come in different flavors. I mean, Cosmos, Polkadot, smart contracts of Ethereum, each transaction requires different types of resources, varying types of resources. Could be huge requests, could be small requests, just, well, to transfer crypto somewhere. You can turn to smart contracts and check dozens of balances. Or inside the smart contract, you could verify some encryption, some digital signatures. So possibly your CPU is smoking already, sizzling hot, and the nodes are simply falling back on calculations, let alone other stuff. Heavier systems, we need to measure at least 4 main parameters. First of all is the complexity of computations, RAM, memory consumption, network size, storage. So how much RAM it will take to process a transaction, set of transactions. Is RAM not a bottleneck? Are transactions not too big? Are they not eating way too much bandwidth of nodes? And how much recording is happening in the storage? So basically disk load, node disk load. How many writing operations are happening, how many reversals there are, if something needs to be reversed, and so on. So there are so many questions out there. So these are the exclusively economic questions, economic issues, which are very interesting in blockchains. And these matters can easily impact the bandwidth of transactions. So for example, some expensive transactions, and miners typically generate empty blocks, they don't pick up cheap transactions, and so on. So they gun for expensive transactions, lucrative ones. So if we're talking about Polkadot's contemporary blockchains, we will not be talking about mining, about this type of networks, because it's not all that interesting to test performance in those networks, because proof of work, POW, it's limiting performance, and it's dragging it to a constant in all kinds of manners. Yeah, there could be some slumps in the bandwidth and in speed, but essentially proof of work regulates network performance. We'll be talking about proof of stake and proof of authority. POS and POA algorithms, the contemporary ones that can process thousands of transactions per second. Let me tell you that stuff like thousands of transactions per second, 1,000, 2,000, 4,000 transactions per second, it's quite fast. That is fairly fast. And as opposed to us, the developers of centralized databases, for them, 1,000 TPS is a ridiculously low amount, because SQL can digest hundreds, thousands, 500,000, 1 million TPS, if you set it up right, the right way. However, let me assure you guys, this is not for master-master. This does not apply to master-master. Take any contemporary system, set it up for master-master replication, so that it can work with the same guarantees of security as blockchain. This 1K TPS will be amazing, will be very good. Even simple, even more basic transactions. Plus, when I was talking about the nature of transactions for DBs, there are certain sets of standard tests. I'm not sure about the name, I forgot it, but they look this way. Continuous selects from the DB generate continuous writing, like inserts, updates, deletes. So there are standard tests, conventional tests, at least two broad standards that everyone is using. These tests are run on multiple machines, and the results are checked. So this is the benchmarking. In blockchain, there's no such thing as a standard test. I mean, we've been trying to make one. I will elaborate about it. Elaborate on it a bit later, but there's no such, just to reiterate, there's no such thing as standard performance test for blockchains. One more thing is finality. Determined finality is even more important. What is finality? In Bitcoin and Ethereum, I mean, in networks POW based, the finality is probabilistic. So there is only a probability that the block that you've downloaded is going to stay in blockchain forever. That somewhere out there, someone is not mining a longer chain than this one. That at some point that miner will not publish it. There is no 100% guarantee that it's not going to happen. There is a certain number in Bitcoin, say over 6 blocks, that are deemed fairly secure, to believe that nobody is going to publish a different chain. Now in Cosmos and Polkadot, finality is determined. Determined as in 100% assurance. The algorithm will say that this block will never be reverted. That's it. If it's ticked, finalized, there's any chain, regardless of its complexity, that comes later will be discarded. Finalized means no other stuff coming through. This is very convenient from the viewpoint of the developer, app developers, product developers. You've waited long enough for the finalized block to appear. That's it. No more worries. Because if some exchange is hooking up to Ethereum or to some fork, Ethereum fork, then in that case, the reorganization of chains, when one chain ceases to exist and the other one emerges, that's a big problem. That's a big issue software-wise, because the software will need to revert this bunch to here and start to pile up the transactions from the different chain. It's called reorg. So if people got their money to the exchange and reorg happened, then their transaction will be cancelled, will be reverted, and they will be penniless, or they will lose that money, or the exchange will lose that money. It's a serious problem. The determined finality says if the block is finalized, if this block is finalized, it's fine. There's no way to revert it. And the speed of this finalizing is essentially the speed of blockchain. Finality, it's a commit in the databases. It's very simple analogy. Commit and rollback. Rollback is reorg, and commit is equals finalized. If you were to run parallels here. BFT, Byzantine fault tolerant. This POW network is not prone to those. This finalization will happen either way. Maybe right now, maybe in a minute, in an hour, today, in a week. If these Byzantine guys are, I think it's less or equal, 1/3. If there are more than 2/3 plus 1 honest guys, honest stakeholders that are honest in this transaction finalization, they're validating blocks, validating information, and finalized, then that tick says that's it. That transaction is never going to be rolled back, unless, of course, there are bugs in the algorithm. Moving further, let me tell you a bit more about finalization in 2 networks. In Polkadot, it works this way. So there are various nodes. Let's say we have 3 validators here. They generate blocks in turn. The first block, second block, third block, first and then second, and so on. So this order, this sequence with which they propose blocks, they're essentially proposers, they propose blocks. This sequence is determined by the first portion of the algorithm. It's called aura in Polkadot. And the second one is babe. Aura and babe is just a way to a point which validator is supposed to generate which block at which time. And then this chain is followed. I mean, it's an independent mechanism. They just do it and they generate new blocks every single time. So they see the transactions from the users and they generate blocks with respect in this rule. Now, in turn, later on, Vitaly Buterin called this algorithm very precisely finality gadget. Finality gadget is basically a separate algorithm, a separate process that is catching up with the chain and asks, is that block finalized or not? Say that block was generated by the first validator, however, it was not finalized. It only becomes finalized when the second validator verifies it, and third one, fourth one, and so on. So when the right amount of validators sign it and say, I've seen that block, I've verified it, I agree that it's valid. In that case, that block is deemed finalized. Now, these signatures, they're supposed to be over 2/3. Well, 2/3 plus 1, so it's more than plus 1, not more, more or equal. So why 2/3? Because if we were to assume that our network is falling apart, say it's split in two, got split in two, one half will be building its chain, I don't know, in the US, and the other one, EU-based, will build its own chain. And not one of them will reach finalization because the quorum for finalization will not be gathered. And when this problem, when the split goes away, when the American and the European networks come together, they will exchange the information about the blocks and they will select, I don't know, the longer, the heavier chain. This is exactly the responsibility of the finality gadget, which one to go for. And just one will survive. And it's never possible to find a situation that these networks will sign both versions. Well, if somebody gets caught, yeah, they will not get away with it. But we're not looking at that right now. So this is finality. Now, Polkadot, this grandpa is a gadget. First of all, blocks are generated, and then finality is catching up with them with big paces, big steps. So bam, and this whole chunk becomes finalized. Bam, another one becomes finalized. Now, if we were to look at Explorer, say Polkadot Explorer, we'll be able to visualize. So I think I've opened Polkadot. We're looking at it as I speak. So two types of counters exist here. The last block, 3 to 1, and 3/18 has been finalized. So three blocks behind. It's catching up within 3 blocks. But that gives me certainty that the last finalized block will never be reverted. So I can use this in an exchange. I can tell the user, okay, your transaction is in blockchain for good. It will not be rolled back ever. In Cosmos, they press for security, higher security for this consensus. Because in Polka, while stuff is getting finalized, you can play around with these chains. In Cosmos, it's not the case. In Cosmos, it says that each block that comes into the network must be finalized at once. So the block is not deemed finalized unless it collects more than 2/3 of signatures. The so-called instant finality in Cosmos. That's the way they dub it. It's not exactly instant. I mean, Cosmos simply does not have non-finalized blocks. It simply doesn't go forward unless validators have come together. So if in Cosmos we do a network split, say they split 50-50, then the network will be stalled. The network will be stalled until the connection is restored, until that split is gone, and at least 2/3 of nodes will be able to finalize the blocks between themselves. This is a bit slower approach because the grandpa is eating away at finality rapidly in big chunks. And in this case, it's block by block. But in this case, in Cosmos, everything that got into blockchain will never be reverted. That's 100% assurance. And in this case, Cosmos applications are more basic. No problems with rollbacks, no problems with chain reorganization. Well, which is best? I'm not sure. It's not clear. Both approaches deserve the right to life. So this is true speed of blockchain. There's another scary slide here. There is L2. There's also L2. Say that there are other nodes with 1 million TPS, and the blockchain is only committing its own state. But we're getting beyond this testing scope. That's another level of testing. So if we're testing blockchain, then the answer as to how many TPS it runs, it features, there's no way to give a short answer. There will be an article required with 3 or 4 test cases and with various numbers in each case. Okay, heavy-duty systems, high-load systems. The manager tells you, okay, can you get me a blockchain with 1 million TPS? And you show him this. So 360 seconds, 1 hour. 3600 by 10 to the power 6 million transactions per second, right? Million transactions per hour. So, but what if during this hour there was some time of outage, the whole network stalled, and then it started working again? And the average is 10 to the power 6. However, unfortunately, the max time was 1 second. For this reason, you only have 1 TPS at this stage, right? And you have 10 to the power 6 TPS here. So which response do you give the asker? The user doesn't give a damn that you have 10 to the power 6. He was sitting there and was waiting for a second, for 10 seconds for a single transaction to be processed. So it's not just the average that's important. Maximal and minimal lagging. That's also very important. That brings complexity to the whole story. When we're talking about blockchains and their performance, who are we measuring performance for? And from the client side, who's sending the request, or the side of validator that generates the blocks? Or saying, grandpa, the finalization happens at the end of the era, or in EOS. So one client might get lucky, his transaction ends up here, and the execution time, the lead time will be shorter. And the other one had less luck, and the transaction performance time will be this. Which one is correct? Which one is the right value? Well, who knows? I can do a test benchmark that will intentionally boost this TPS or bring it down, depending on my intentions. So I can I can generate any TPS I want, depending on how I play with my benchmark. So be very skeptical about these figures, about these TPS figures. It all depends on the operation reality, operation context. Say you have 100 transactions per second. Are you sure that all these transactions per second have been loaded? Maybe they're taking a break. Maybe some of them are not loaded properly. So what is the load of that node, say? You need to maximize the load to improve the speed. Maybe there could be more TPS than you actually see on the screen. So there's no simple answer to this question, alas. Right, what do we do? How can you bypass all that? How can you test blockchains? Say you've developed your own blockchain, say Cosmos or Polkadot based, and you want to test it, performance-wise. Now, what you can do is you can run the blockchain on a local machine and simply script several transactions into it. Script in, say these many TPS. Okay, this much TPS. This is a make-believe number. It does not reflect the actual operation speed of the blockchain that yours might evolve into. Internal codes how much the blockchain can process to state and record to state. Well, it's just one figure that will depend on a whole bunch of external factors when we move from to the actual network from a single local machine. You could try launching testnet and measure everything out there. It's close to real life, right? So you'll get dozens of nodes from multiple partners, and you will proceed to load them with stress test. That's also a good thing. However, blockchain is stateful, meaning that the resources will be piling up. And when you run the same test in a month, the figures will differ because the nodes will be loaded, the more RAM will be busy, more storage will be occupied, and so on. So the golden middle, your single local machine, Docker, and say launched a dozen containers. They will not be, they'll be kind of siloed, and you can measure their operation, their interoperation, and run a scenario to benchmark. This could be more or less reproducible. I mean, you can run the same test on the same machine in 1 month, and it will be the same. So this is closer to the actual testing. However, you will still run problems, because ideally, in real-life situations, to test real-life situations, you will need to test the network split, some lags occurring between various nodes. Some machines might experience downtime, malfunctions, so you will simply need to code it into your scenario. So what are you likely to end up with? Well, most likely your DevOps will be delving into the broad-scale testing of blockchain. You'll be writing various scenarios, automate this unwrapping so that it's always happening in the same way. And accordingly, your DevOps will have to leverage a whole software suite to make sure that the testing is reproducible. Unfortunately, there's no other way to do it. Distributed DBs are tested the same way. There's no other options to do it differently. The closer you get to real-life situations, the better. It's clearly it's an expensive endeavor. It costs a pretty penny. But if we want to make a simple solution and test our own blockchain, what are the technical requirements? What are the specs? First of all, we need to be able to reproduce the same configuration on a number of validators, around 100. So with contemporary consensus, 100 validators works okay. 1,000 validators, well, we will spend a whole lot different amount of time for coordination. So these contemporary blockchains are inoperable today. They cannot operate with 1,000 validators. So this blockchain solution must be deployable. I mean, you should not be able to ruin anything with your own hands here. Say you might make a mistake, and one machine will affect other machines because it's too slow compared to the others. You will need to be able to collect metrics from the node blockchain and from the clients. If you want to be able to visualize the results, we will need to draw charts. We'll need to compare these charts. Because like I said, there's dozens of metrics out there. It's system resources, finality, block generation. You'll need to look at all of them to not miss a thing. So like I said, reproducible conditions, it must be able to emulate, well, some packet loss here. It must be able to emulate poor network conditions between validators that generate blocks. Ideally, this should be working in a cloud provider, in various cloud providers, because like I said, it's heavy-duty software. Blockchain nodes is a fairly heavy-duty piece of software. And essentially, you will not be able to use dozens of machines in Dockers because, well, simply your local machine will die right there if it tries to do that. So, and we want the benchmark to be more or less standardized. I mean, these requests to blockchain that are executed, they should be more or less standardized. Our approach when we were testing Polkadot was this. The standard layout of testing for blockchain is transfer. It's just plain transfer of a random transfer of a random number, random amounts of tokens across random number of nodes. This is statistically even. It generates random addresses and it sends random amount of tokens. We had address 1 with X currency. The second server received half of the X of tokens. The third gave half of that amount to the second one, and so on. Essentially, this is the attempt to make a very even load on the nodes. Even, non-heavy duty, without any spikes that come and go. So yeah, ideally that test would be desired. And of course, it must be embeddable into your development process. If your coders committed some new changes, they accelerated some network layer, and you test the same test, and you see the improvements or lack thereof, if there's a failure. So what can you read up on this? Well, I have a link of various testing distributed systems stuff on GitHub. So it's very useful for testing distributed systems. There are several ready-made conditions, and that presentation was born because I was doing the overview of these solutions. One of these solutions has been written by us to this specific end, for this purpose. It's an open source stuff, mixed bytes tank. It was born specifically by these challenges. We needed to resolve these challenges when testing the network. What I'm saying is, this is likely, this is very likely something your DevOps would have written, would have coded, if you had them test your blockchain under development. And there is a Hyperledger caliper. A caliper can deploy, set up blockchains for its own hyperledgers. It does it in Dockers on the local machine. Unfortunately, it can spin stuff around. It can emulate packet loss, but it only does that on the local machine, on an LM. It collects metrics. It shows the loads, measures success rate, transaction rate throughput, latency, and so on. There is white block genesis. I did an overview 18 months ago, so maybe some new stuff emerged that I'm not aware of. You can do an Ethereum fork, proof of stake, proof of authority. We did that, and you can use white block genesis to test that Ethereum fork. So in this case, they will deploy it on their machines. They will run the benchmark, and they will provide you the results. This is a commercial solution. Our solution, the mixed bytes tank, is built. Well, the most important product we leverage is Terraform. Terraform is essentially a piece of software that allows you to code something in Python. I mean, provisional code. Okay, get me a virtual machine with that many, say in the US, 4 cores, 8 gigabytes of RAM. I mean, you can select some EVS DigitalOcean. You can select a virtual machine to be launched, and say launch it in America, in the US, some T2 X large, and do it in a cycle, so that the Python script could create you 100 VMs. In this case, yeah, please make sure you run setup on each VM. So this is a gizmo to automate cloud operations. The orchestrator is another name for it. An orchestrator is a piece of software that rests here. Say AWS is here, and it creates the VM, sets it up, runs some benchmark on it, and then it kills it. So you can also say destroy in the script. So everything you're clicking with the mouse in AWS, Terraform helps you automate. It's an open source thing, very convenient, extremely convenient piece of software. It cleans up after it's done. If the cloud supports packet loss and geography emulation, say, come up with a poor network between these transfers. The packet loss can be emulated, or put this machine into China and this one to the US. All of that can be scripted there. Also, mixed bytes tank can launch multi-thread transaction sending. Embedded metrics can also be possible. Say there are nodes that generate blocks. They are deployed by separate validators. There are nodes that do benchmarking. I mean, the ones that spin these scripts that are loading blockchain with transactions. Also, special VMs are tested on Prometheus with charts generations. So all the nodes are preset like this. They will send their load information over here. The memory load, the CPU load, and so on. All of this is deployed in a single package. It works, I don't know, the test operation is 5 minutes, 10 minutes, 1 hour, 2 hours. And then everything is cleaned up. I mean, it kills the whole stuff. You can save the graphs, of course, or you can kill the graphs if you don't want them. Also, it generates logs and core files. We needed it to detect the node downtime when they crashed, the crashing. And we wanted the logs from that crash right away and look into the issue. Look at the errors that caused the crash. So this monster came into being. When we put it together, we thought, all right, well, essentially it's a testing product. We've published it. Well, feel free to use it. With a high degree of probability, if you don't want to use third-party solutions, well, get prepared. Your DevOps will need to be prepared to a huge endeavor measuring the TPS, measuring the performance of blockchain. Performance measurement for a blockchain is a whole amount of work. It's a whole amount of workload because automation of cloud deployment of every cluster on each VM will need to be aware of other machines, secret keys, pairs of keys will need to be generated. Some initial setup will be required, writing up this set of validators, and so on and so forth. There's tons of workload. I mean, there's no well-known best practices solution, apart from the 3 I've listed before. Right, let me show you something else. By the way, the finalized block in Polkadot, check this out in Polkadot. In no such thing in Cosmos. Like I said, every block that the network accepts is finalized right there, right out of the box. So you can simply plan for next transactions, roll on next transactions, and not be afraid of rollbacks. If you're online and you're watching the network condition, well, you will have to use complex systems like parsec, reversals. It's a serious project, Ethereum tracking. Now, if we were to talk about how we see the ideal blockchain testing process, well, since we have this workshop, let me show you how Polkadot is tested. We've not been dealing with Cosmos so far. Maybe at some point we'll make a mixed bytes tank for Cosmos. So there's a bunch of tests, and they're fixed on the single version of Substrate. It was quite a long time ago. Now it became faster. The tests look like this. Say 21 validators have been picked. A localized cluster in a single location. Stable connection, no network lags. This is loaded by benchmarks. Several benchmarks. Say one is running 20 transactions per second and sends 1,000 transactions. Then 210,000 transactions are sent. And then further down the line, 400 transactions, 100,000 transactions are sent with a pace of 400 per second. Then the test is run, is configurable in the mixed bytes tank, and the set of charts is generated. This is the CPU utilization of nodes. There were spikes up to 100% at some points. So it's clear that some nodes have peaked in their computational power. Another important metric here, so this finality delay. Finality delay, it's very important. So that finality delay is essentially a serious indicator for blockchain's performance. How much the finalized block is lagging from the most recent one. So this pace of block generation it's clear. Polka, Cosmos, they generate a block every 5 seconds, every 6 seconds, every 3 seconds. The speed is clear. However, the finalization speed, the lagging behind of the last finalized versus the most recent 2 blocks, 3 blocks, well, that's a very important metric. That's a fairly important metric. You can check it out here. There's a standalone graph for that, separate graph for that. So no TPS mentioned ever in any location here. No numbers of transactions. There are some metrics that can show you indirectly how many transactions have been processed, how many of them are seen in the block, but that's not too interesting. That's not too interesting. These TPSs are not indicative of blockchain's performance. The finalization delay, this is the most important bit. For Cosmos, well, this thing is much clearer. There's no, for finalization comes, with the block emergence once it gets into the database. So these figures will be more reliable. You will not need additional metrics for that, for Cosmos. But for other blockchains, for every finality gadget, for every consensus algorithm, the performance tests differ. So please don't think that there are some generic common solutions. Each blockchain is to be tested separately. Okay, so say everything was fine. Then we launched test 2. 49 validators, same routine. Same profile, more or less similar. Then 49 validators, and we distribute them across locations. Europe, Asia, North America, 2028 respectively. The same load is generated by the benchmark, and we check out the performance. When the load spiked, the delay spiked as well. The nodes faced additional load. Well, they took some time to process it, then they accepted this load, and so on and so forth, etc., etc. So you see many profiles of testing here. And it was right there until, yeah, 100 validators. 100 validators. It's a very heavy-duty test. Geographically distributed cluster, 7% packet loss. 7% packet loss is a very poor network performance. I mean, like, there's a pigeon eating away at your cable, like, every single second. So 33, 33, 34, 200 TPS from the benchmark side, 10,000 transactions are sent. And I believe, yeah, after 2 hours, the testing stopped. This was a fairly crude substrate, to be honest. Well, the summary of this, blockchain testing for performance, same as distributed DBs testing for performance, is a major piece of research with dozens of use cases, test cases, with various load profiles. So a bare number of TPS for a blockchain network will not tell you anything. Let me give you an example of how the profile, testing profile might look like. Let me scroll it down to that. Well, essentially, you simply write up the setup procedure for the tank. Say a procedure to register 1,000 random accounts. No, not register, but maybe transfer tokens to 1,000 random accounts. And there is a function that sends transactions per se, commit transactions. The rest is handled by the tank. That's its first part. The second part of it, Ansible scenario. Ansible, the DevOps know what I'm talking about. That's the tool for automatic configuration of any machines, any batches of machines. It's quite a lot of that stuff here. So essentially, this is the scenario that Polkadot deploys. With the right amount of validators, it records the peers, it regulates the peers, the blocks. This is the scenario to kick the network into gear. So whether you're using the tank or not, your DevOps will be writing something similar to this. Ansible, you will definitely get something similar to Ansible to deploy your automatic network. So that's it. The rest is handled by Python that pieces this whole thing together. You can't even pitch that as a project because this is a code that simply assembles multiple tools. That's it. There's no way to pitch it, to introduce it as a standalone project. Now, to summarize, roughly speaking, please be very skeptical about TPS as a point of discussion. Request details. What exactly was measured? How that TPS number was arrived at? What kind of measurements it took? What kind of network was envisaged? How many validators? In what conditions? What were the transactions? That's the minimum set of questions you need to ask when you're given a TPS. Say, splitting a network in two or killing it altogether will give you 0 TPS. If you're testing, please don't forget to test for different numbers of block producers because the results will be different. 20 nodes will find a harder time to coordinate than 3 or 4. It will take much more time, much more resources. Monitor system resources as well, because at some point you might overlook the hardware issue. Maybe your consensus is more powerful than the hardware you're using. Maybe you have some space for maneuver there, but say the CPU is not able to process more digital signatures, or you're tossing so much trash into your blockchain that your RAM is running short, and this could be a bottleneck preventing you from seeing that your benchmark that your blockchain could be even faster than you see it perform. So when this user sent from the JS the request to buy something, and then they're trying to pluck up enough patience to wait for the finalization to come, or to wait for the ban of the transaction. Not 1 second, not 2 seconds. Please don't hope for that. Not any contemporary blockchain will give you that fast a response. Not Ethereum, not Cosmos, not Polka. Don't expect that. The waiting time could be 3, 4, 5, possibly 10 seconds. All interfaces should be looking at these numbers as indicative. These numbers have a theoretical threshold, speed of light. The speed of light is the fastest your nodes can communicate between themselves. Even if you have a 1-bit block, you will still find the speed of light as the threshold. The validators will still need to coordinate that single byte. So don't trust any fairy tales about millions of transactions that people throw at you. That is doable. However, you will need to sacrifice something. You will need to sacrifice some security matters. Right, so that's it. So please be very skeptical about the TPS people tell you, and be very careful in disclosing your TPS. So this is the main essence of this workshop, of this presentation. I'm ready for your questions now. Thank you so much, Sergey. Yeah, we've had some questions that have come in. Please keep those slides shared. I will go to the HackAtom chat. The first question is this. The price paradox, is it happening? Adding additional power to the network. If the entities existing in the network select their own route, it might reduce the performance. This was something you told at the beginning of your workshop. Well, Bryce paradox. Could you repeat the question once again? Okay, paradox, Bryce paradox. Do you know what it is? Well, there is an explanation what it is, kind of in parentheses, adding additional power to the network in the condition that the entities moving in the network are selecting their own route, and that could bring down the overall performance. Yeah, that's exactly what I've been referring to. The P2P network issues. You're sending the transaction into the node. It will take some time for it to reach the validator. Some time to reach the validator. This time could be different depending on where you're sending the transaction. It's this paradox happens. It does occur in distributed system because these transactions will reach the block producers at different times, and those block producers are also located in different segments of the network. Now, it might take a second to deliver this block to this producer, and in 10 seconds, it might take 10 seconds to deliver that block to an even nearer producer. The P2P network works like that. If there is no homogeneous performance of this network, like a constant in centralized clusters, I say a dozen machines who are nailed down to the floor with fixed IPs, with rigid network configuration. In these systems, there is such thing as a constant time. Such thing as a constant for delivery time. In peering, in blockchain, this does not work. In P2P networks and blockchain, this route is important, indeed. The client will need to wait for the transaction to be delivered, to be mined, and when they until such time that they receive the information about the final block and the block got finalized. This is not just important for that transaction, but also for the finalization of the block. I hope I've covered that question. Right, he's hoping as well from fork log. So there are more extensive questions from fork log. Thank you for your presentation. So why are those live graphs are not collected by generators of blockchain? It would be interesting to see the live load of Polkadot at this time. Well, the load is not displayed, of course, but this data is collected under the hood. So if you're a decent validator, you will definitely have something like this installed. You will be monitoring your validators. All contemporary blockchains, as far as I'm aware, Polka, Cosmos, I might as well even show that to you. Say if I launch the substrate, the Prometheus server is launched right out of the box here. So all these metrics for blockchain can be launched like this. Prometheus, your node. Well, observing such metrics is a very interesting thing. It's a curious thing. Well, some validators might make this information public. There is an interesting story that I've forgotten to tell you about. The game of states in Cosmos. Cosmos came up with it. This is a competition between validators. It's kind of a competition between validators. Transactions are sent to the validators, and then the metrics are selected from this, are collected from these validators, and then the rankings are assigned. Who is the first place, runner-up, and so on? Who generated the most blocks? And the winners can get more tokens, or can become testers, can become validators with a higher status. Say it's a great thing in the real world, like get 10 banks into a competition who will be competing for the transaction speed of the clients. This will not be possible in the real world. In blockchain, it's possible. So these blocks, validated by validators, can be checked by anyone else. This is a great thing that the Cosmos guys have invented. We did that for EOS network. That game of states was great, a great success. There was some collective graph, and you could actually see which validator was more performing, was least performing. Well, making the production validator graphs publicly open. I'm not aware of such practices. So the monitoring is ongoing. Be sure of that. The third question: have you considered the possibility of using Kubernetes for some of your tests? Yes. Yeah, we have. It's just at the time it was more convenient for us to roll with Terraform and DigitalOcean because it was right there from the box that you could have written something like I've shown. Let me pull this up. Where did I have it? In Ansible, in Grafon, you could, in the config file, you could simply indicate packet loss and the location of the machine. It was much more convenient than Kubernetes. Other than that, you can use Kubernetes just as easily. From Grafana, you could. The tank does not care whether the VEMs are deployed or should be deployed. It's important for Terraform to have the connector to this gizmo here. Could be a cloud connector. I'm sorry if I'm not careful, if I'm not precise in my answers, because I'm not exactly a DevOps guy. Although each blockchain developer is acting in part as a DevOps because no problems will need to be solved, and that requires at some points resolving the DevOps kind of challenges. There's another question. I believe that well, the audience is very heterogeneous, and the questions are different. So cover them at your discretion. So this is the question. Next question: if I want to interact with Cosmos network, would it be sufficient to address any validator using a specific protocol? Well, validators are normally protected. Protected simply for the reason that their external users are not bombarding them with these requests. Validators are typically hidden between full nodes. So the validators on the networks might have their own networks of validators so that they can exchange blocks rapidly across them among themselves. And externally, say, not internally, externally on the internet, there are full nodes that are not generating blocks, but they are receiving the information from validators very rapidly, so that a new block can occur. And then they pass on the transactions to new transactions to the validators. The transactions come here, come over there, and then the P2P network is used to feed these transactions to the validators from the full nodes. The validators themselves are hidden. So this is the inner perimeter, because these are the machines that store the keys, the graphic keys. In case there is a, well, I say, game of states that contests are mentioned, validators even sign a paper saying, acknowledging that there could be hacking attacks against them as validators, because they're doing it for testing purposes. There isn't even legal paperwork that they need to fill out. Say one validator can attack the other validator, trying to win. So we see a leader, and okay, the other guys can pitch in and try to crash him. So validators build these security perimeters, hiding under the full nodes. Full node can be launched by anyone, by you on your local machine easily. So you cannot go directly to the validator. You can go to the full node, which will talk to the validator. The full nodes are out there on the internet. They're public. In this particular case, whenever I'm getting this information, I'm looking at the website here. And in this case, in Polkadot, this whole interface, and it's available in IPFS as well, I'm talking to a specific node. So which particular node I'm talking to, which IP address, the same goes, well, similarly to the MO with my local network, like 127.0.0.1. No problem whatsoever. Okay, one of the hackathon people is asking you the testing protocol and the checklist. Can we look at that anywhere? Well, there's a link in the presentation, in the slide deck. this is basically our report on that grant. This is this testing protocol. I mean, how many instances there were, what type of instances these were, the speed of benchmark, the number of validators, the pace at which they were loaded, better charts than displayed here, more precise, high resolution, and you can read up on the read up on the results of any of these tests. This is public info, yeah. We got a public grant to generate it, so yeah, of course we were supposed to disclose it publicly. It's as simple as that. Okay, right. So we will need to provide the links to the guys so that they will find an easier time tracking this. Okay, there are some off-top questions as well. Let me pull them up. Well, this is the last question anyway, so I'll ask it. What can you tell about Solana? They claim that the network can process 50,000 TPS. Have you been working with them? Well, not really in depth. I mean, we're not looking in depth into them, but these dozens of thousands of transactions per second, they're not impossible. Solana is a project where the team they're really crazy about low-level stuff, about optimization. And they are writing the kind of blockchain that is about fast transactions. The node work in parallel. The nodes work in parallel. The contracts are built specifically in such a way so that a single node can collect as many transactions as possible, and the processing is as fast. So it's kind of like a single chain blockchain. So they're resolving the scaling problems not as Cosmos or Polkadot by huge number of blockchains, each blockchain handling specific type of tasks, and they're interacting somehow between them. Solana said, no, we will take a single chain and we will simply tune it to perfection. We will tune it to perfection, to max performance, and they're doing a great job while at it. So they've really done a powerful chain. 50K, you can definitely get that. Blockchain can do 2,000, 8,000, 10,000 transactions into a block. So 50K per second is possible. But when I was telling about these magic numbers people throw at you, I was referring to the figures of 10 to the power of 5, 10 to the power of 6. So this is hundreds, millions of transactions per second. I mean, there's only so many transactions you can stuff into a single node. 50K is a big number as it gets, is a big number as it is. So yeah, the hardware can be improved and so on and so forth, but unfortunately, the speed of light kind of story is not going away. This threshold is there. So regardless of the speed, regardless of the number of transactions you can cram into a single node, the unification, the coordination will take time. There's no, otherwise you're losing the BFT capability. Visa is running 24K TPS. Visa, and possibly MasterCards is running something like that. So yeah, Solana can definitely run the processing system for the entire planet. Well, that's a loud statement to make. Well, why not? 24K plus 24K makes 48, around 50. Server loads with Yandex and Mail.ru, search engines, they can generate dozens of millions of events per second. So they're not scary numbers I'm talking about here. Right, so as we were discussing here, there was an elaboration for the previous question. How can a DDoS attack implemented against a validator? Will it be a single validator that will get kicked out of the entire network? Well, if you're doing a distributed denial of service attack against validators, well, first of all, you will need to get access to them. And like I said, in this setting, it's not going to be possible. It will be a DDoS attack against the full nodes that are concealing the validators. And then the validators will get that. Because, well, if the validator is sticking out and it's visible, well, typically, yeah, you can just send conventional JSON RPC requests, make a DDoS like that, like a balance request with an amazing speed. they will use the resources to that, and they will the block production will fall. But having killed one validator, you will not do anything bad for the network. If you kill more than 1/3 of validators, then yeah, you will basically stall the blockchain. So DDoS against blockchain, well, it's quite possible. Moreover, this DDoS attack can be run quite efficiently because the blockchain nodes are processing transactions and they're spending quite a lot of resources. So any digital signature verification is 2 to the power of 256. Well, hundreds of dozens of thousands of signatures cannot be verified on rank file on common hardware. Yeah, you can DDoS a blockchain network. Blockchain is a kind of a dark forest. So many mysteries. Right, that was the final question for the day. I mean, for this topic. The off-topic questions, well, Sergey, you can go to Forklog, check out the chat box. But there is stuff like, what do you think about this project, that project, NFT? Well, some more generic, general dialogue. So we're running a hackathon here. We're trying to explain to the guys how the networks operate, what kind of problems they might face, and how do you solve them. Thank you very much, Sergey. Get connected, guys. The next workshops of hackathons are coming soon. Participate in HackAtom RU. We have a huge full prize pool. Add to that chat. Many developers are looking for teams there. Collect the bounty, collect the prizes, win. So anyway, looking forward to seeing you at